Hello, ladies and gentlemen. Welcome to coronavirus video, I believe, number 4. So in this video, I am introducing Kepler's laws and the implications of Kepler's laws. And he basically has 3 of them. And so we will start with Kepler's first law. So you can see Kepler's first law here. We've got, if I'll just read it, all satellites in a solar system. Okay, so it has a star and an object in the middle. They all the satellites orbit in a circular or elliptical fashion. Quite honestly, it's actually elliptical because you can have the special case of an ellipse where the 2 different axes are equal, and that just makes a circle. And so all satellites will orbit in an ellipse. Okay, and the star planet that's central to the system will be at one of the foci. So you can see the example here. This guy right here is at one of the foci, and then by its very nature, the other foci will have nothing at it. Okay, so at one of the foci, it can be at either one, but whichever one it's at, the other one will not have a star or a mass of any kind at that foci. Okay, Kepler's second law. Kepler's second law basically says, and when he came up with this law, it's a little bit before some of the orbital mechanics were fully understood. I believe it was before Newton had finalized his universal law of gravitation, etc. So it's kind of wacky. But basically, what he said was that if we have a satellite or a planet that's orbiting a star, it will sweep equal areas over equal times. So you can see the example here, right? So all of these areas, right? So you see A, right, are equal areas. And so if you did the calculus to kind of like do the integral and figure out what the area in this little area here, this little sweep is, you'll find that the A here is equal to the A here is equal to the A here if all of your times are identical. Okay, and so the shapes are not congruent in that they're not shaped the same, but the areas that they sweep will be the same. All right, and so if you think about this for a moment, right? You see how way far away at what's called the apogee, right? So the apogee is when a satellite is furthest away from a sun, versus the perigee, which is where the satellite would be closest to the star, to the sun. All right? And so by its very nature, right, this guy's further away. Its radius, quote unquote radius, is further away, right? And so what ends up happening is that it ends up slowing here. So it slows down speed-wise here when it's furthest away, and it speeds up when it's closest. Okay? And the easiest way I have found to understand this second law is this right here. Angular momentum is conserved. Okay, so regardless of where you are on this ellipse, right? Remember Kepler's first law. That the angular momentum of that satellite about the star that it's orbiting. Okay, so the angular momentum of that satellite about the star will always be the same. And so linear momentum here is the same as linear momentum here is the same as linear momentum here. Sorry, angular momentum, right? And so this will be the case. L1 will equal L2 at apogee and perigee at anywhere. But just FYI, at least at the level of physics that we're at, remember we simplify things. Okay, these will be the only 2 spots, the apogee and the perigee, that you'll be asked questions on. Okay, and so because it basically makes the geometry a lot easier if you ask questions about just those particular areas. All right. And so if we treat our satellite as a point mass, and it truly is like a point mass because, the distances between the stars and planets are huge, right? And so we know that R1 cross P1, so that would be the radius vector, right? The distance vector times the momentum of that object, right, at that point, right, will be equal to the other radius cross momentum. Okay, and so at apogee and perigee, right, this will be the case. And again, this apogee and perigee are going to be the only two cases where we will have to analyze something with respect to Kepler's laws. All right, and so this will be the case because at this point right here, I am going that way, and at this point right here, I'm going this way, and so the angle that I make is 90 degrees, and so my cross product, right, will be the sine of 90, which is 1. And so that's why R1 P1 will be equal to R2 P2 at the perigee and apogee. Okay, Kepler's third law. Kepler's third law basically says it's basically a ratio, right? And he came up with this law by observing the celestial bodies, right? So observing all the planets orbiting the sun, and he found that there was a particular ratio of periods and the distance away from the sun of these different planets. And basically, I don't try to memorize that particular ratio. All I do is I remember when something is in rotational equilibrium, like stars and planets wise, right? I know that what? I know that my FC will be equal to my FG. This is the same for, remember when we had orbital velocity, when we calculate the orbital velocity. This is very similar, okay? It just, he takes it kind of a step further by looking at the ratio of periods, radiuses, all right? So we know that FC is equal to mv squared over r. We know that the universal law of gravitation tells us that Fg is g big M little m over r squared. Okay, and then we're just going to do a little bit of algebra here, right? First off, we're going to cancel out the mass of the satellite itself. And so this tells us right away that the mass of the planet or whatever that's orbiting a star, okay, has no relevance to its period, which is kind of weird, but true. And so what I did is I then plugged in an expression for the velocity, right? And so the velocity is basically equal to the circumference the planet travels, the orbit, right? The linear distance of the entire orbit, which would just be the circumference, right, of that particular planet, okay, divided by the time it takes for that rotation to occur. And that's the definition of period, right? Is the time that it takes to repeat a pattern. And so, and the pattern is going around a star one time. And so the velocity is going to be equal to 2 pi r over t. And of course, that's going to be squared. And so we have a little bit more algebra to do, right? And so we're going to multiply that out. We get period. The period drops down to the bottom, and then we're going to put our r. We're going to cancel out some r's here and there. Actually, I think r squared and our r cancel out to r here. All right? And so that leaves us almost there. We're almost there. Bada bing. Here is Kepler's third law. What Kepler's third law more or less says is that the ratio of the distance away from a star of a planet cubed divided by its period squared is the same for every single planet in the system. And so I'll say that again, okay? This ratio that you see right here, this g m over 4 pi squared is the same for every single planet in a star system. And so in our solar system, right, if we had the mass of the sun, right, and of course we knew G, right, every single ratio of the, so if I took Venus and I plugged in this distance away from the sun, cubed it, and then divided by the period around that sun, okay, it's going to be exactly the same for Earth. It's going to be exactly the same for Uranus. It's going to be exactly the same for all of the celestial bodies, even the asteroids that are rotating around. Okay, asteroid belt goes at the same period all the way around. Okay, and so that is Kepler's third law. Okay, let's delve just a tiny bit deeper into Kepler's third law. And let's look at how two satellites in the same star system are related. And so I have planet number 1, and I have planet number 2. And you can see subscript-wise, right? And we know that this is true because this is what we derived in the previous slide, right? That this ratio is equal to a constant based on the mass of your star. Okay. Well, what can we do? Well, we can say that if we set those equal to each other, right, we're going to have this ratio. And so if you're looking at two different planets in a star system, you can basically set these ratios equal to each other because they are equal. They're both equal to G big M over 4 pi squared. So in the orange over here, you can see a question that you might actually encounter on an exam. Question that says if one planet has an orbital radius of 3r in a period of 2t, and so this would be, call this radius number 1, period number 1, and it asks what is the orbital radius of a planet that has a period of t. So this would be my t2. So all I have to do is set up my my equality, right? Two planets. These are going to be the same. And then I just plug in my numbers. And so I get a 3r cubed, and I have a 2t cubed, and I plugged in my t right there. And so I need to solve for what? I need to solve for my radius for that second one. So I pluggy chuggy, and I get my r2 is equal to that. Bada bing, bada boom. And you can basically do the cube root, right, of that, and then there you're going to get your ratio relative to r.